This chapter is on heat.
I love the heat.
So here's your thinking question. Suppose you have 2 cups of water, one's hot and the other's cold. How is the cold water different from the hot water?
There's no such thing as cold. Trick question.
Trick question. No. Cold is the absence of heat.
You mean the absence of heat water?
Hot water has more energy. Describe the motion of the molecules in each.
It's faster.
Faster in the hot. What changes would occur if the hot water was changed into steam? Turn into steam. Faster. More energy, faster. Okay, what's the common scales used to measure temperature?
Fahrenheit, Celsius,
Kelvin.
Yes.
Kelvin's number 1.
That's 217.
Kelvin's SI.
73, bro.
Is it 273?
Yep.
217?
273.
It's 2 something.
Which scale has the largest degrees?
Kelvin and Celsius are the same degrees.
But which one is largest?
Kelvin.
No, they're the same degrees, aren't they?
Newtons.
Well, and Fahrenheit. We have 3 scales, right?
Oh. Kelvin is highest.
No, isn't the size of the degrees of
Yeah.
Kelvin and Celsius the same?
They're
Yeah.
both infinite.
And they're larger than Fahrenheit? Are they?
Numerically, if you go like on a number line, Kelvin.
No, but like in 1 degree Celsius, 1 degree Fahrenheit, is it Celsius degree?
Yeah.
Yeah. Celsius and Kelvin. You tried to
But if you're talking about like a number line, Kelvin.
We're not talking about number lines.
What are we talking about?
The size of degrees.
And which one's bigger?
Celsius and Kelvin are the same.
Because if you think about going from the freezing point to the boiling point, Celsius goes from 0 to 100, and Fahrenheit goes from 32 to 212. There's fewer ticks in the Celsius scale, so each tick is worth more.
Makes sense.
Yeah.
But if it was 1 degree Celsius.
Temperature means the average kinetic energy of the particles, and the average speed is used because all particles do not have the same speed, and the speeds change as the particles collide, so they use the average. Internal energy, it's on Edmodo.
I'm not going to print notes because I printed notes for every chapter and I get like 70s and 80s, but the one chapter I didn't print notes, I got 103.
Internal energy is the energy of a substance. The energy a substance has due to the motion of the particles and the position of the particles. So kinetic and potential energy contribute to internal energy.
So if you drink a lot of sugar, you get internal energy.
Forms of internal energy.
Hot sugar.
I need to make sure.
There's no such thing. You mean absence of heat sugar?
Warmer sugar is better than not as warm sugar. Because absence of heat is 0 degrees Kelvin. That exists. That's what that is the world.
Turn up, Miss K. The volume.
Trying.
Ronnie, you should write a song called Turn Up
Okay.
the Volume.
The energy associated with particle motion in an object is known as internal energy, which is proportional to the object's temperature. There are 3 kinds of internal energy: translational, rotational, and vibrational. Translational energy is due to the motion of the particles in an object. Rotational energy is due to the spinning of the individual particles about an axis. Vibrational energy is due to the stretching and bending of bonds between the particles. Interestingly, radiation produced in microwave ovens causes water molecules to rotate rapidly, and this rotational energy is converted into translational, rotational, and vibrational energy in neighboring molecules. As a result, the food in the microwave is heated.
Oh.
Yeah. Creates friction with other molecules and heats it up.
Not talking about friction, I'm talking about-
Do thermometers change the temperature of a substance being measured?
Yes.
How?
Because the friction.
No, because the thermometer is a different temperature, so sticking it in there would cause it to change.
Right.
Because
Uh-huh. Well, it might be ice water. They put it in ice water. So if the thermometer might be different temperature than the actual substance you're measuring, so then it will change the actual temperature in the water. Yeah, okay.
Good call, buddy.
How can you minimize the problem? Yep, let it be in there for a while. We stir it, get those molecules a little bit. Or just let it acclimate in there. Come to an equilibrium.
Smell. Usually since it's
Temperature must be measured when thermal equilibrium is reached. Always read a thermometer after it has stopped rising or falling, and at this point, equilibrium has been reached. So there's been no more transfer of heat that way.
Ooh, another one.
Another one, a thermal expansion.
Please close your
Ooh.
Ooh, zippers.
Yeah, that does bother me.
You
Almost.
have
She'll probably have the calculator.
Temperature changes can cause materials to shrink or expand at different rates. Because of this, engineers must design bridges, buildings, and other structures with ways to adjust to thermal changes without weakening the structure. On long bridges, for example, expansion joints may be used. Expansion joints have interlocking fingers that permit the bridge to expand on hot days, reducing the gaps between the fingers. The length of a 400-meter bridge may vary by as much as 10 centimeters due to temperature changes in the course of a year. Without the joints, slabs rigidly fixed to either bank of the river would push against each other and buckle, distorting the shape of the bridge. Since concrete fractures rather than flexes when stressed, structural damage can occur.
Ooh, wow.
The wood dividers between slabs of concrete in a driveway or sidewalk provide a similar cushion between expanding materials.
Yeah.
Oh, that's why you play Foursquare.
So that's why my growing up, we had a big patio on our outside our backyard, and there was just a big slab of cement, but they didn't put the lines to allow for the expansion, so there's big cracks in it. Just from,
My slab is small.
even there's a crack. Hmm. Okay, so expansion of mercury changes the reading in this thermometer. So and we don't have mercury thermometers, we have alcohol thermometers. But how much does a small change in volume of the mercury result in such a large rise inside the thermometer?
The activity. Is that right?
Expands. So they move faster, get farther and farther apart, so it expands and goes up the volume. Or goes up the thermometer and changes the volume. No. Oh.
You're at 150. 150 what?
Did you really game for 2 pounds, or did they just like precise? Really?
America.
Calibration depends on fixed temperatures. So when we use our logger probe, the steel temperature probes, we always calibrate it, and we depend on fixed temperatures. So you always want to measure like the freezing and the boiling point because we know what those should be. The 3 common temperature scales: Fahrenheit, Celsius, and Kelvin. Everyone knows the freezing point: 32 degrees Fahrenheit, 0 Celsius, 273.15 Kelvin.
Did they teach you any Fahrenheit in Germany?
Would we have to convert from Fahrenheit?
Probably not.
That's not
212 for boiling point, 100 degrees Celsius for boiling point, and then 373.15.
Did they teach you any Fahrenheit? That's all that matters in America. Fahrenheit's what's better. Fahrenheit's the life.
So what's it meant by absolute zero?
No.
You can't get it.
So,
Oh, ooh, ooh.
They came very, very close. They've never been to absolute zero.
Motion stopped among particles.
Right. Particles stop.
That's right. I took earth science.
Yeah, we did.
Can we watch it again?
No.
Give me a computer or something.
Right. What'd they call it? They had the computer, computer chip that it ran faster and it could compute so much more without having the heat produced.
I would like to point out that my title is
0 Kelvin. So suppose the pressure and temperature of a gas are plotted, shown, and then it's extrapolated to 0 Kelvin. What does that suggest about pressure at 0? Right. Yeah, I don't know that they'll ever get there. Yeah. So pressure is equal to 0, absolute 0.
We have to
Okay, the Celsius temperature, or Celsius Fahrenheit temperature conversion. And really, I don't ever memorize this. I always know that you have to multiply or divide. I use 1.8 instead of 9/5. But you either multiply by 9/5 or multiply by 5/9. And you either add or subtract 32. So I always pick 212 and 100. You got to get 212 and 100 to equal each other. So you either got to multiply by 9/5 and divide by, or multiply by 5/9 and add or subtract 32. It's for anatomy. Yeah. Okay, to find Kelvin, you just take the Celsius temperature and add 273.15. One day it was 40 degrees Celsius at the top of Mount Blanc and 40 degrees Celsius, negative 40. Yes, this is where the one point where it's exactly the same temperature.
Except which place was more absent of heat?
They're the same.
They're the same?
Right, negative 40 and Celsius and negative 40 Fahrenheit is the same. Mm-hmm. So convert negative 40 Fahrenheit to Celsius.
Negative 40 times 9/5.
9/5, and then add 32.
Minus 32.
Add, isn't it?
You can go either way.
No, because you gotta. If you minus 32, you gotta do that first.
Order of operations.
Add 32, and what do you get?
So big.
Yep.
So
Convert to Kelvin again.
Take Celsius and add 273.15. Yeah. So what's the Fahrenheit temperature? Oh, what is the Fahrenheit temperature equivalent to absolute 0?
We don't know because we can't get that.
Well, 0 Kelvin is how many Celsius?
273.5. No.
Negative 273. So negative 273.5 times 9/5 plus 32. Yep. Negative 459.67. They have. What'd you have? 273.15 times 9/5 plus 32. And what'd you get? Negative 460. Yeah, which is pretty close. I don't know. I don't know why theirs is a little different then. What's the Celsius temperature when the temperature is 100 degrees Fahrenheit? You guys know how to convert. Let's go on.
We do not know how to convert yet.
Right. I think you guys were all good on those questions.
Oh yeah. Our earth science teachers were top notch.
Yes.
Mr. Barker's the one.
Okay, let's stop there.